Alright everyone, welcome to my HKNVideoReview review by me. So the topics I'll be covering will be pointers in C++, dynamic memory allocation, and class-based inheritance. Prerequisites for this specific presentation is that you have knowledge of C++ up to STL's data structures such as stacks and queues, and you also have knowledge of the class structure in general in C++. Alright, so pointers in C++. In C++ specifically, memory management is easier for the developer because of the fact everything is pre-compiled. In C++, there is a concept of a stack that inserts memory addresses of function calls and variables made during compilation. There is also a heap for function calls and variables made during runtime, which ties into dynamic memory, which I'll go over later. Pointers in C++ are variables that can store a memory address of a variable of a specified type. So, for example, in my int main over here, I have an int var equal to 10, and then I declare a pointer, which is equal to the memory address of var. I'll go a little bit more in depth with the syntax of a pointer, but for now, all you need to know is that a pointer is declared whenever an asterisk is next to it, and whenever it points to a memory address of a variable specified by this ampersand sign. And when I attempt to print out the contents of var and my pointer variable, I will get the value of var, but also the memory address of var because the pointer is pointing to that variable. In C++ we also have a special keyword called no pointer, which is basically the default value you should always set your pointer, or else it will point to garbage value that will lead to undefined behavior. And by doing this, you can add custom checks to check if your pointer points to nothing, or if your value gets deleted at some point during your program, so it can prevent unwanted errors. So some traits about pointers. Each variable in C++ or just in programming in general has a byte size. For example, ints can store 4 bytes, floats can store 4 bytes, and doubles can store 8 bytes. And the same is true with a pointer variable. However, it follows a different rule, where the size of a pointer is dictated by the computer architecture. For example, in a 32-bit architecture, because the max amount of bytes that it can store is 4, pointers are 4 bytes in size. And the reasoning for this is because pointers need to be able to account for every single possible memory address in the program, similar to how an int can manage a range of numbers. And the same thing with the other variables. Thus, pointers are sized based on the architecture to handle any memory address. So pointers store memory address of variables, but it's still possible to access the data of the variables we point to as if it's a copy of that variable, but we'll go more in depth with that later. And pointers are also able to represent custom classes and structs implemented as well. So to use pointers, you can either use these two formats, where you either have declared your type of value that your pointer is pointing to and your pointer name. You can also add the ampersand either to the left next to the type, or you can add it to the right next to the variable name. Both are correct. For accessing the memory address of a pointer or just a variable in general, you can use the ampersand in front of the existing variable to get the memory address. And this is an example of how to do that. To use data within your pointers, you can use the ampersand sign against the variable name so that you can dereference them. For example, I've declared a custom class right here with a constructor and also a function. And in my int main, I declare 2 sets of variables and pointers. One is for an integer, and one is for the class itself. As you can see, I can add the ampersand sign next to the star sign next to the variable name, so that I can declare it as a pointer, which is applicable to any class or struct you declare in C++. And I point it equal to the memory address of the previous class, let's slurp Jane Juliet, that I mentioned earlier. And then in C++, you can dereference these two values so that you can access the variables of the pointers. So for example, in this example, I dereference the pointer value, which is pointing to a LARPing message, so it prints out 10. For classes themselves, there's a lot more leniency and methods in order to dereference certain attributes or values. But in this case, I chose to follow the normal rules where you dereference the object first, put that in parentheses, and then you can call functions as if it's a normal variable. So over here it prints out the message that sum and larp does. So when it comes to classes, when you declare them as a pointer, there are two ways to dereference them. You can either use the star method that I showed earlier, where you can dereference them in parentheses to dereference them as an object, and then call normal functions via the dot. Or you can use the arrow sign to access specific variables or attributes, such as functions, within those classes. And this works for structs as well. And both are fine. Now we can talk about references. References are another type of variable in C++ where they are an exact copy of an existing variable with the same memory address and variable value. So in this example, I declared an audio that is equal to a string message, and then I declared a reference variable which is equal to that variable. And in order to declare a reference, it's similar to getting the memory address, where you just include the ampersand sign in between these two variable signatures in order to declare it as a reference, similar to a pointer. So in this example, I print out the values of each variable as well as the memory addresses of each variable, and as you can see below, they are pretty much identical. One important thing about references, though, is that they do not have a supported type, such as null pointer. So it is important that you always initialize them, because if you don't, you will get an error from C++ as there's no way to declare them without being initialized. Now that we talked about the references and pointers, we can now go into how pass-by works in C++. Pass-by, I of course mean whenever you pass parameters in a function, and in C++, usually when you pass parameters in a function, by default it's passed by copy, but it's possible to use the previous variable types we mentioned earlier in order to pass by different types. So for example, in my first example, I have a pass by coffee instance where we declared a enough larping message that should overwrite the value of anything we pass in, so that in our main it will print out that modified message. However, in pass by copy, the output is still the same variable, because by default a variable passed in the function is a local copy that goes out of the scope when the function ends, so there are no changes that affect the output. However, there are ways to circumvent this, which is where pass by references. By adding the ampersand sign next to the variable, you are declaring a reference variable that is equal to any parameter passed in. So when you pass this larping variable into enough larping, it declares a reference to that variable that has the exact same signature and memory address, and this could actually modify it so that out of scope, the changes made to that local variable in the function affects what occurs in main. There's also an additional pass-by method called pass-by pointer, which in my opinion is mainly just useful for terminology and for the exam that comes up. And as you can see here, by dereferencing the pointer that you pass in, it actually modifies the original variable value, similar to the other methods. It's very niche, but it might show up in Prog 2 specifically. Now that we talked about pointers, we can talk about dynamic memory allocation. In C++, there is a heap that essentially serves as a way to store allocated memory. This is done via pointer manipulation and special keywords. Dynamic memory can create special runtime variables that store very large objects and makes managing memory manually to prevent memory bug errors. However, you need to delete any memory that you allocate within this heap when you are finished using it, Or you will get segmentation faults, which are errors that occur when memory is mishandled via byte offsets or accessing data in a vector that doesn't exist. To initialize dynamic memory, you just need to use a new keyword next to the type of variable you're pointing to. For example, I declare a string pointer as usual, but then I set it equal to a new string, which is called Yo on Jane Juliet, where this pointer now points to dynamically allocated memory that's not actually on the stack, but on the keep. And then you can use it as normal compared to a normal variable. And to delete dynamic memory after use, you just need to use a delete keyword in order to delete memory that was made with a new keyword. If you don't have a delete keyword to delete allocated memory, you get a segmentation error. In most cases, primitive data types like ints in C++ have destructors to effectively manage this, but you would have to define the definition for complex variables such as structs in classes. Also, you can get a segmentation error when accessing data that's already been freed. So in this example, I've declared a int pointer larbine, which is set equal to a new int array of 2, which I'll go a little bit more in depth later on how this exactly works. And I've set one index 1 to 68 and deleted my dynamic array. However, when I attempt to access variables again from that array, it'll give me a segmentation error or a freed error because that data has already been freed. Alright, so now we'll talk about dynamic memory allocation in a list, also referred to as a dynamic array. To store a container in dynamic memory, you need to use basic array types. It's similar to the last slide, where you use this format for new type n, like for the right side of your pointer initialization, where n is the array of a type that is n in size. Then to delete the allocated array after use, you have to use a special keyword, again, like similar to the last time, except you just add the brackets at the end of delete. So in this example, I've declared a int pointer, which is set equal to a new int of 4 or a new dynamic array of size 4. And I initialize the values for this class, and then also iterate through them normally. Note that you don't have to really dereference the variable itself, because it's already indexed, and you can directly access it. And at the end, you just use the delete brackets keyword in order to delete your pointer. This might seem a little trivial, but in reality, this is actually insanely useful, as you'll see later on when we resize arrays. And it is used as the baseline for many of the famous classes that you know from C++. And speaking of which, we'll talk about classes. When dealing with dynamic memory in classes, such as like using dynamic arrays, for example, you need to declare a custom destructor in order to manually delete the memory outputted. So you probably are a little familiar with this, but again, I'll do a little refresher on what a destructor is. So in this example, I have a class stack, which is meant to be a basic representation of a stack, where I've declared an int pointer to a size and an int pointer to an array. You can note that they're pretty similar. The only difference is the value we put in. So on the constructor, whenever we input s, we can set our size equal to a new int s, as well as our array to a new dynamic array of size s. And we can do pretty much all of our stuff like in here, like our initialization functions, like for pushing to a stack and etc. However, when your stack class goes out of scope, you need some kind of special destructor, and a destructor in C++ is a supported way in order to add some custom behavior to a class whenever it goes out of scope. This is normally here by default, but you can declare it physically by using this squiggly line next to your stack call, similar to a constructor, but with no parameters. And in your destructor, you can just declare your delete keywords, so like for your dynamic memory you want to delete on deletion, in order to prevent any segmentation errors from occurring. And when you're attempting to add to a full array, specifically a dynamic array, you need to resize the whole array by reallocating new space to it. And there are two ways to achieve this, where you either copy the whole array directly, or you copy each element of that array. Or, in simpler terms, making a shallow versus a deep copy. In all scenarios, making a deep copy is easier and the most preferred way, and I'll go over that right now. Shallow copy arrays are pointers pointing to the same address. So in this example, there's an int pointer new array which points to a new dynamic array of size 5. and then we've declared a new array variable that is equal to an old array that we've declared in the past that has the same size. So in them, it looks like this, where your array points to this array of variables, but your new array just points to the memory address of array. It has the same data, but the deletion of the old array will delete the contents of the new array, which can cause some segmentation faults or unintended error, which is where deep copies serve the best use case. Deep copy arrays are pointers where each individual value is a unique new element. So in this example, we declared a new array again. However, this time we've just made an iterator so that we iterate through every element of the array, and for each element of the new array, set it equal to that new element. So in memory, the array has a pointer to a list of variables, but a new array has a pointer to that same list of variables. However, each element is independent of the other one. So essentially, it's the same data, but the deletion of the old array will not delete the new array since it has new values. And for resizing, I have an example right here, which is in the stat class I mentioned earlier, where it returns a bool to see if it passed, but to be honest, in this case, it would always return true, where we push an integer I. We first check if the array is null pointer, and if it is, then we increase the we set the capacity equal to 1, and then set the array equal to a new int capacity, where the array is now a size of 0. If the size is equal to capacity, meaning that the amount of items in the list is equal to the capacity or total size of the array, then we have to resize it. In this scenario, we can just scale the capacity by 2 and declare a new int pointer to a new int array of the new capacity. And then we copy every element of the old array into our new array, and then we delete the old array and set array equal to new array. In this case, we don't delete the contents of new array because those contents are immediately being stored within the old array. And then we set the top element of array equal to whatever we push in, increase the size, and return true. So just remember that when dealing with dynamic memory in classes, you need to first initialize a deep copy, and then also make sure that whenever you're resizing your array, to always override the values of the old one correctly. And just a final tidbit, pointers are more useful in C++ when dealing with extremely big external classes from modules or libraries that would take up a lot of space in your compiler. And now we're on to class-based inheritance. It's similar to Python, where you can inherit classes by indicating the next to your class declaration. However, you must define its scope. Listed here, I have a table showcasing all the different types of scopes that are available to you. So, you are probably familiar with public and private. The public scope allows you to access all public and protected variables and functions of an inherited object. And if that confuses you, I'll go a little more in depth on what exactly that means later on. And a private variable means that I cannot access anything for the inherited classes. And one key indicator that we'll go over later is that private equals a has a relationship, while public equals an is a relationship between the base and derived class. There's also the protected scope, which makes it so that only the base and derived classes can access public and protected variable and functions of the inherited object. Meaning that whatever you inherit from a base class, only the class deriving it can access it. Okay, so for this example, I have a dancing class, which would serve as my base class in this example that would be inherited from, where it has all the basic components of it, such as the getters as well as the constructor. And I've declared a new class called BlueSturdyKit, which inherits from the dancing class. Note that the scope of my class is public, meaning that it can access all these public variables right here. All these public functions right here. In other scenarios, you might see private or protected, meaning that the scopes we mentioned earlier would apply here. Same thing for the scopes that you declare for your variables as well. If you, by default, classes of course have a private scope, but you can also see protected here sometimes, indicating that it can only be derived within the future classes. And over here, I have pretty much inherited from the dancing class and can access specific attributes from it, which I'll go a little bit more in depth right now. For the constructor, it's pretty much the same, except we also have to declare the constructor for our base class, because if we don't pass in the variables that we have obtained, then there could be some errors in the future. So my Blue Sturdy Kid constructor takes in two parameters, being the name and the song. And then we declare a colon right here in order to declare that we're going to access more constructors that we've inherited. When you're inheriting multiple classes, you can just add like commas and then list them out. But in this case, I only have one, so I just pass in my song variable into dancing, which is valid because it's a string. For getting specific functions or overriding functions, in a basic scenario like this, where there's no special keywords, you can just declare the variable name off the bat and it will immediately override it, and then you can pretty much do whatever you want inside it. In this case, we have decided to return the name plus the original song. In order to get variables or functions within the base class, you typically need to have the dancing scope resolution operator to get it, as long as it's one within scope and accessible to get. And over here we have like an example of our code running, and as you can see, it outputs successful output by first getting the name as well as the original song within the dancing class. Note, when you're calling a constructor, you always must call the constructor of the base class unless a specific scenario arises, which we'll get into later. And you also need to use reference variables such as getters, or and make sure that you use the scope resolution operator in order to resolve this. Now we'll talk about the virtual keyword. The virtual keyword in C++ is a special keyword for classes that allows for defining functions that you would want to be overridden in a derived class, and is primarily used for runtime polymorphism, which I will discuss later. And note, you will need to use the override in children classes to ensure proper virtual class use. This is pretty much similar to the previous example where we've manually overridden a class. However, in this one, you need to do a little more manual work, where first you declare a virtual function, which already is defined. But in the same example in the derived class for Blue Sturdy Kid, you have to add the override signature at the end in order to override it. Typically, this isn't necessary, but this is like again necessary for questions where the base class uses virtual keywords for the functions, or as I said earlier, when you want to use runtime polymorphism, which I'll discuss later. Now we'll go over abstract base classes. Abstract base classes, or as I like to refer to them, ABCs, are classes that act as an interface and are not meant to have any defined behavior. They are meant to be defined and must be defined within inherited classes, and they utilize pure virtual functions and also allow for polymorphism similar to the previous examples, which again I'll discuss later. So in this example, I've declared an abstract base class where I have a class called invincible character, where I pretty much have the same syntax as like my dancing class. However, I have this two new keywords right here. I declared a virtual void print name function, but I set it equal to 0. This essentially means that it's I declared it as an abstract a pure virtual function, meaning that whatever class inherits it must override it and must declare it and define it. So in the last example, you don't need to override it, as you can just use the base function, and you only needed to do it whenever you wanted to add custom behavior. But in this case, you must always define it because of the fact that it's a pure function, and if you don't, then you get a specific error. You can also declare you must also declare a destructor as well that's virtual, so that whatever class inherits it via when you're using multiple base classes or when you're dealing with dynamic memory, your constructor knows to call the default destructor. That way it doesn't get any weird errors in the future. It typically doesn't come up that often, but it's just important to have as a default so that you don't get any specific weird bugs within C++ in the future. So in this example, we've declared a LARP variable which is equal to this derived class, we can be bees, and then we've pretty much passed in all our functions as normal, and then we print the name. It's able to be called because we override it within the we can be bees, and it calls all the variables and messages we wanted. And now that we've discussed pretty much everything that comes to inheritance in form of the big three methods, such as normal inheritance, inheritance with virtual functions, and then abstract based classes, We can now talk about the diamond problem, which I think is the most important topic you should remember from C++. So when inheriting the same class in two different classes, it is fine since we only inherit from the base class once. So in this example, we have a video game and a Duck Hunt class and a Fortnite class that inherit from video game. But if you were to create a class that inherited from both classes, such as Duck Fort Hunt Night, which inherits from Duck Hunt and Fortnite, you will get an error because you attempt to create the base class multiple times. And what I mean by that is when you declare Duck Fort Hunt Night, for the constructor, you have to declare this long list of constructors with their respective parameters, and you have to also declare a parameter for the base class, which normally works. But because you're calling the constructor for Duck Hunt and Fortnite, within those constructors, they also have a reference to the base class as well. There's like 3 base class calls, meaning that this will create an error because the constructor doesn't really understand which reference to the video game class it should use because it's ambiguous. The solution to this is to just use the virtual scope for inheritance to prevent recopying of the base class. The virtual keyword just ensures that whenever a class inherits it, it pretty much just goes one layer up via upcasting. Upcasting is when you're declaring a class of a type, and then you're indicating that whatever class it's based off of, you can go to that base class. It's a little complicated, but it'll make sense when we go in for polymorphism. So in this example, we've declared a virtual public video game for both Fortnite and Duck Hunt, which are the 2 classes that Duck Fort Hunt Night go over. And now that we declared them, we can just declare a constructor for Duck Fort Hunt Night and pass in the parameters as so for Duck Hunt and Fortnite. It's a little incorrect because I forgot the parameters, but just imagine it's still there. So in this scenario, it will call Duck Hunt first, and then call the public constructor for video games within here, but it won't call the one in Fortnite because there's already a constructor initialized for the video game base class. Thus, the diamond problem is solved. This is the solution that C++ typically pushes when you're dealing with a diamond problem within C++ 11. Now for the last problem, we'll talk about polymorphism. It's basically stating that since classes derived under a base class is a base class via publicly, it is possible to utilize their pointers to point to the original base object reference and then utilize their functions. So, as I stated earlier with the scopes, a public makes it so that whenever you publicly inherit a class, it is that same class. With private, it's a little more different, but it's essentially saying that it can't really access anything from the base class, so it just has it as a reference. In a private scenario, typically you can't really inherit from the base classes and use them in polymorphism, so it's recommended that you use public. So in this example, just imagine that I've made a ABC class called Terrible Endings, and then I have a list of derived class that virtually publicly inherit from Terrible Endings as well, such as Chainsaw Maid Ending, Modulo Ending, and JJK Ending, and I declared the objects for each one. If you wanted to create a program that would call the display ending function within all of these functions, because it's a pure virtual function that each of them inherit, you need some way to sort of just parse them and maybe even like compare each type of base. However, in C++, you can use polymorphism to create a container that references the terrible ending class as a pointer to store classes of multiple types. Essentially, we've declared a vector which stores terrible ending pointers in this variable called larp. The reason why this works is because of a concept called upcasting and downcasting. Upcasting is when you're taking a class and storing it as a reference of its class that it's inheriting from. Downcasting is when you're taking the base class and calling it like a type of its its future classes, which is typically not recommended. So we recommend that you use upcasting for polymorphism. So in this example, we've used upcasting to declare a vector, and then we can push back all of these variables since they are a type of terrible endings. And then we can basically say for each element within our container, we can call the display ending because all of them have this virtual function that is already declared. Just remember when using polymorphism, you need to make sure that all the classes are of the base class and that you correctly upcast it by using endings pointer. This is my HKN Prog 2 review, and I hope you guys enjoyed it and learned from my lesson.